Hello, my friends. Welcome back. So in the previous videos, we did talk about how we can improve and optimize our throughput and delay and some of the techniques that we could use to improve our timing. In today's video, I want to be talking about the remaining two techniques for timing optimization, which is register balancing and then the last one would be reordering paths, right? So let's talk about the register balancing. So when we talk about register balancing, as the name suggests, the idea is to redistribute the logic evenly between registers to minimize the worst case delay between any two registers, right? Right. So this technique should be used when, the logic that you're implementing is highly imbalanced between the critical path and another path or some other paths, right? Because the clock speed is limited by only the worst case path, right? So when you distribute the logic that you have between multiple paths, then it should actually improve your timing. An example of this would be like a very simple example. So I just copied the template from our previous examples here. So I'm just gonna go we have an input A, and let's just copy this. And we're just going to call that B and C as well. And then we have O data, which is also 4-bit. Again, we're not really talking about bit procedures and everything. It's just so that you get the idea of what we're doing. And so just like before, I'm just going to do it the quote-unquote incorrect ways and see how it goes. And then we can show how we can optimize it. So let's say you want to add all these three numbers, right? Go A plus B plus C and save the result in O data, right? Okay, sounds good. So one way of doing that, which is not really a good way, is to have logic 4 minus 1 down to 0, and then have RA for, or reg A for register A, right? And then do that for the other ones as well. So this would be D, and then this would be C, right? And on here I go at every rising edge of the clock. Reg A, for example, gets the value of A, right? Because you don't want to miss the values. And you can do the same for B and C. So I'm just going to go B is this guy, and then C is this guy. Okay. And then I go my O data, right? O data. That is, and let's just shift these guys. Just not what I meant. Okay, here. And then here that we could just go, let's just copy this, bring it down here, is this plus this plus this, right? So this is one way of doing this. And as you can see, one path is from input A to register A. The other path is from input B to register B. The other path would be from input C to register C. And then the other one would be from all of these, do the calculation, and then put the result in O data, right? Which is not the best way of doing this. And so obviously this is not really a good design. How can we improve the timing? This is a technique that we call register balancing, right? So instead of doing that, I can basically, let's just copy this and then go here. And we're just going to comment this out. So we can go, I don't know, define reg A, for example, is A plus B, right? Get rid of this one. And then reg C, C. So you're registering that. And then here you go. The out data would be register A plus register C, right? Which is this guy in here. Doing it this way, so you're distributing the logic. You remember how we were performing 3 addition operations, right, in one clock. And now there is only 2. So you're doing 2 in here, and you're doing 2 in here, you're doing 1 in here, and then you're doing 1 in here as well. So you don't really change the number of add operations that you're doing, still 2 adds, but these are done like in separate clocks. So that's fine. And so you reduced your critical path, or what worst case path delay, from 2 forward addition to only 1, right? So in theory, you should be getting like twice as clock cycle, like a clock. Like you probably should get, like, in theory, half the clock cycle that you used to have. So this is, as I said, like very simple register balancing technique, right? So hopefully this was clear, and if not, please do not hesitate to reach out and ask me in the comments your questions. And then the other one that I wanted to talk about is just like copy that over here, and let's get rid of these. Let's get rid of these. I don't think I'm gonna need this, but we'll see. We'll see what's gonna happen. And then the other technique would be reordering paths, right? So we have some path and we want to reword them. And an example of this would be, or before getting to example, when we talk about reordering path, it's obviously like the 5th strategy that we're talking about for when it comes to minimizing the critical path delay and improving the timing. And this technique is usually used whenever multiple paths combine with critical path. So when you have like conditions, and like you're making decisions based on, I don't know, some conditions that you have. Usually that's how it works. And so with this strategy, we will only be concerned with the logic passed between any given set of registers, right? It will be more clear when I give you an example. So let's say we have like still A, B, and C as our inputs, right? And then we can go and say input, input wire, we can go condition A or condition 1, so that it's not really related to A in here, not confusing. And the other one would be condition 2, right? So let's say we have 2 conditions, and when we have like these 3 inputs, and we want to assign based on the conditions that we have one of the inputs to the output, right? Let's see how it works. Again, as always, we're gonna like implement something, like any logic that you want. So I can just go if condition 1 is true, right? Begin, and then like I'm just gonna put the end here, and I'm just gonna go O data is I don't know, let's say input A, or any condition. So if condition A is true, then that's it, finish. Assign input A to the output. And then I want to go else if, and now if else if, which means if condition 1 is not true, and now I'm just going to go condition 2 is true, and my input C, just like putting in brackets, input C is less than I don't know, 4 take decimal 4 or 3. I don't, doesn't matter. So if input C is less than 3 and condition 2 is true, then begin, and then end. I'm just gonna go O data gets the value of C, for example, and we can go else begin. O data gets the value of C. Then and. Oh, okay. Let's change that to B. So it's in order. So if condition 1 is true, then what's happening is that I'm assigning the input A to output else, which means if condition 1 is not true, then come back in here, check condition 2. If that was true, and if C was less than 3, then O data is B, right? And then like if neither of those cases are true, then O data equals C. So when you look at the implemented design in here, what's happening is that the critical path, I would say it's something between C and output. Because first of all, we need to do like this comparison in here, right? And then we are going through like different levels because like we talked about this in the previous video. It's a priority encoder, right? So when you're coding like this, like this condition has to be checked. And then we get back in here and then we'll look at it and we'll say, okay, condition A, condition 1 is not true, condition 2 is true, and this is less than that. So like 3 different conditions, we have to meet all of them. And then if that was not true, then come back here and then assign C, right? That's why I'm saying the critical path delay is probably between C and the output. Good practice here would be like I open this guy in here so I can show you a rough approximate of what's going to happen if I implement this. So let's say my input A is here, right? And then I have my condition 1, right? And then let's say we have condition 2 in here, and then we have input C in here, and then we have, I don't know, input B in here, right? So if condition A is true, right? If condition A is true, if condition 1 is true, and then what's going to happen is that I'm just going to put like a big multiplexer in here. Is just the mux. So the output gets the value of A, right? Let's just assume this is what's going to happen. And then here I'm just going to go compare, like I need a comparator here. So we're just going to compare. One of the input to the comparator is number 3. The other one is C. So C comes here, number 3 comes here. If that's the case, right? If this is true, if C is less than 3, right? And condition 2 is true, right? And there is one more. We should say that there is another AND gate. And we want to check that condition A where condition 1 is not true. Because if condition 1 is true, then output is A, right? So now I'm saying if condition 2 is true and C is less than 3, and condition 1 is not true, then the output would be B, right? So I'm just gonna put this in here. B goes here. Now, like these are select lines, right? Like you can tell I don't really have to do this again. And then if that wasn't the case, then C goes to the output, right? This is, and let's just like put the array in here. This is how it works. That's what I'm saying. Looks like the critical path is between C and the output, because like it goes through this comparator, and then this guy in here, and then this guy in here. So 3 different stages, and these stages, they have to be done sequentially, right? You have to go through this first so that you can calculate this. And then once you have this, you can calculate this. So you have to wait for like 3 stages of conditioning to get to the output. So obviously this is not really a good practice for coding. So what's the solution? How we can modify this code to have like a better design, right? And improve the timing. So I'm just going to copy this, comment this out, and then I'm just going to go here. And I want to reorder the path. This is the name of the technique, right? I'll show you how we can do this. This can be a bit tricky, but once I explain it, it's going to be super easy. So all I'm going to do is to cut this and put this here. I'm saying if condition 2 was true, right, and C is less than 3, right, then output is B. Else, if condition A, where condition 1 is true, right, then out is A. Again, it's the exact same logic. Like I'm not changing the functionality of the design. I'm just reordering different paths, right? And I'm not going to touch this. doing this, you're actually improving your timing, right? You may ask, okay, why? Like, how is that even possible? You didn't even change anything. But as we talked about this in the previous video, this is like priority things, right? So when we talk about priority, implementation actually matters. So let's see how we can implement this. Like if we implement this on FPGA, how it's going to turn out to be. Okay, so here for the second implementation, we have our condition 2, we have our condition 1, right? And then we have our A input, we have our B input, and then we have our C input. Let's see how it works. So when we implemented this, we say, okay, if condition 2 was true and C is less than 3, then do that. So let's do that. I'm just going to say this would be mapped to this guy. So if condition 2 is true and condition 1 is not true, because this is what that condition meant, right? And C is less than 3. So we need to have a comparator here. So we have like the comparator just like before. One of the input is like a fixed number 3, and then the other one is input C. So if that's true and this condition up here is true, right? Which means that we need to perform a logical AND between these two, right? And then if this condition was true, what's going to happen is that I'm just going to put this, like this would be a select line, and the input C would be selected to be assigned to the output. Sorry, like these lines are not really straight. Oh, this was better. Anyway, so you get the idea. So if that's the first thing. And if that wasn't the case, then what's going to happen is that I'm going to say if condition A was true, so if this was true, then no matter what, so no matter what, input A will be assigned to the output, right? So like this is one group with its select line, this is like another group with its select line. And then if that's not the case, then B is assigned to the output, right? I guess. And sorry, C is assigned to the output. And so we can actually go here. I think I made a mistake here. It was supposed to be B. So if I go back, sorry about this guy. Okay, so if this condition was true, B was supposed to go to the output. So I'm just gonna correct this. Okay, so B goes here. If condition A is true, but I'm just gonna come down here. If A is true, then no matter what, if condition 1 is true, then A is going to be assigned to the output, right? And then if that's not the case, if neither of those are true, then like C is going to be assigned to the output, right? And when you look at this, sure, we still have like 3 conditions, but this and this. So I just, if I select these in here, so this condition and then this condition, they are being done in parallel, right? So you don't have to wait for one to have the result for the second one, right? You can do that in parallel, so that saves you some time, and thus you can improve your timing. That's why this implementation and like a very simple reward rig would help you significantly to save some time and improve your timing for your design. Hopefully you found these techniques useful and you learned something from it. If you did, and if you enjoy this content, please like the videos, let me know. If you have any questions, please do not hesitate to ask in the comment section. I'm responsive. I can guarantee that I can answer your questions. And well, at least I try to answer your questions. This is better. And as always, thank you for watching these videos. And yeah, see you guys in the next video. Take care. Bye-bye.